where we have a tag team talk from Carius and Vassilios Tsounis from ETHZ.
All right, ready? Okay, works. All right, hello everyone, I'm Vassilios.
I'm Carius.
And today we'll be talking about locomotion research, which we've been performing on the single-legged hopping robot. And the research goals for this platform basically are twofold. We want to test a new actuation system, which is cable-driven actuation. And we want to basically do research in policy search and demonstrate sim-to-real transfer. Now, the two main approaches which we take for this include trajectory optimization and reinforcement learning. But today we're only going to talk about the former. So system overview quickly. We've nicely baptized this platform as Kepler. Kepler basically stands for cable pulley driven legged robot. It has 1 degree of freedom passive base, which we measure using a linear draw wire encoder, and a 2 degree of freedom planar leg with only hip and knee flexion extension. And basically, to get a quick overview of what we're talking about, the system is, as you can see, the V-rail. We've done a series of experiments trying to jump as high as possible. This demonstrates basically the capacity for the actuation to perform highly dynamic maneuvers, whereas other experiments which we've done in trajectory optimization, you can see on the right, is trying to implement, trying to basically verify experimentally some of our research results. So, actuator design, very quick overview. It's a cable pulley system, meaning that it consists of 2 elements, the cable and the pulley. The pulley is a capstan drive system, if you're familiar with this type of system. It consists of 2 elements, a sheath and a pulley, which are basically, we're using it as a transmission system, only transmit at a very low gear ratio of roughly 1:5, and thus having high torque transparency with on the joint. So, to implement the actuator, we're using all off-the-shelf components. Very simple motor, encoder, absolute encoder, and off-the-shelf motor controller. And to test, really, to show before we move on to trajectory optimization, we did 2 sets or 2 battery of experiments. The first is a high jump, where basically we achieved the maximum measurable height of 1.22 meters. This was over a repetitive hop of, you can see 2 consecutive hops there in the graph. And then there's a pie chart roughly of the of the energetic losses. And then the second battery of tests includes a longevity test, where we actually executed the system for 42 hours, almost consecutively, because obviously we have to sleep. And then basically Jan will talk about now how we're using it for trajectory optimization research.
Yeah, so we use this as a test platform for trajectory optimization. So as a bigger picture of my project is really, we want to find a way how we make this quadrupedal robot, for example, traverse some really rough terrain and only specify the goal distance, and it should figure out by itself what's the best path to take without us specifying what kind of contacts it should use, which gate, which sequence. And as you've heard from the previous few talks, this is a hard problem. Now, the typical way how this is approached, at least over the past few years, is that we combine a free-floating dynamics formulation subject to external forces, and couple it with contact constraints that are both put into a general purpose optimizer, like SNOP, IPOpt, if you're familiar with those. Now, unfortunately, those optimizers have problems with solving those kind of difficult constraints because they don't exploit the full structure. Now, one of the ideas that we want to propose with this project is essentially, why don't we move the contact effects, the constraints, directly into the system dynamics and pass this into our specialized optimal control solver, and thereby we actually retain some of the very nice properties, like the nice scaling invariance to the contacts. In the next slides, I'll show you a video of how this could look like, and in particular, I've implemented a morose time-stepping scheme, which essentially fuses the free-floating dynamics together with contact effects like friction, impact, into a single formulation, and pass this to a completely unconstrained ILQR solver. Now, how does it look like? We can, for example, impose a cost on the base height of this hopper, and for 2 different costs, it will automatically find a jumping motion without us pre-specifying that we should have different phases in this motion. I also extended the system with an extra degree of freedom forward, and by just specifying the goal, same plane implementation, it could come up by itself with a various step forward hopping motion. Now, the final goal of this project eventually will be to apply the insights to a full quadruped, and here you see 2 videos of other research going on in our lab to which we will contribute. And if you have any questions on this, or particularly about our two projects, please see us around during the next few days. And we have 2 posters hanging around here, which should be up soon. So we're happy to talk to you and take your questions. Thank you.
Much. Do you have any questions? Pranav.
Yeah. Can you tell me a little bit about your how you incorporate the contact in your dynamics simulator?
So this is not something super new. So what I'm using morose time stepping, the essential idea is you solve the free floating dynamics subject to the contact constraints, unilateral hard contact constraints with friction and with impulsive forces on a velocity level. And this is essentially, if you know Bullet, for example, as a simulator, this is also something very similar what they do. And
so you're not making the optimizer solve for the constraints, but you're making the dynamics solve.
Exactly. This is the key point, because this optimizer has issues, at least what I perceive, with if we give him the dynamics and then the contact constraint on the same level. This is not made to solve it. Whereas we thought, why don't we use a specialized routine to solve the contact separately from solving the optimal control problem?
I'm going to use my prerogative as the moderator to let Michael Poza ask a question.
So are you familiar with like what Katja Mambauer was doing with multiple shooting methods for trajectory optimization? So this sort of strikes me as very similar to that. I mean, where you put the contact back in the dynamics, and now you're doing, I mean, ILQR or really whatever at that point. So I almost feel like the right is a predecessor to the left, you know, historically speaking.
Possibly in some sense, but I haven't seen much of like exploiting this into a single formulation using all the derivatives that you can get out of it and inputting it into ILQR. But I guess it's a valid point, and we should talk about this offline as well.
Yeah, I think that this would be a great discussion to take to the whiteboard in the break. And anybody else that's interested, please, Ali, can you set up?
Okay.
All right, let's think.